So the first thing we should do is install Docker. You probably already know how to do it, but let's go through the steps anyway for Ubuntu. I have a virtual machine here, so I'll be using that. So I'm just going to go to the browser and search for the instructions. Okay, Docker C. Okay, there we go. Instructions. I'm just going to copy paste them. So the first step seems to be to update the package repository. Okay, so these packages allow apt to add a PPA, because we have to use an external PPA. Here we go. Install the validation keys. This is just the check. Okay, so here we actually add the repository. Update our package index again. And finally install the Docker components. This will take a while, so I'll just skip it. Alright, so the Docker installation is completed. Let's see what, so now we can basically perform a step to see if it's working, which is this step over here. It's a hello world, running a hello world image. So the first time you run an image, Docker pulls the image, it downloads it, and that only happens the first time. Okay, so this is our validation for Docker. Now there is one additional step. Since we don't want to run Docker all the time as sudo, I don't see it being necessary. What we can do is just add our user to the sudo group, to the Docker group. In this case, user. Now you have to log out and log in order for these changes to come into effect. So let's do that now. Okay, so I've logged out and logged in again, and I'm going to try the command again just to make sure that my normal user has Docker permissions without sudo. Great, it seems like that's the case. Ubuntu enables the Docker service to start up at boot. If that's not the case in your distribution, you can use a systemctl command. First of all, to check the status of the Docker service. So that's sudo systemctl status docker. So in our case, it's actually running, and it's also enabled during boot. If you need to enable it, it should be in your system, in your distributions documentation, but you just need to do systemctl. You probably just need to do systemctl enable docker, if you're using systemd, obviously. And that should enable the service. If you want to start the service, then the command is start. You also have restart and stop. Okay, cool. So next let's download Yocto. I'll be switching to my host system, so I'll not be using Ubuntu anymore. I'll be running Arch, but it should be the same regardless of the distribution you're running. I have made a collection of scripts which help us enter the Yocto development environment. The URL is it's a GitHub repo at hubshuffle/yocto-docker-quickstart. So let's visit that web and clone the project. Before cloning the project, let's just go through each file does. So we have start.sh. This script basically just enters the Docker environment. It has some arguments which you will see later. Clone Yocto is to be run once, just to clone the Yocto Pokey. It clones Pokey, it clones the meta-raspberrypi layer and the meta-open embedded layer into a separate folder. The home directory just has your normal user's home directory, but this will keep persistence inside the Docker container, so you can maintain things such as the bash history and also SSH keys or anything else. Now, the Docker folder contains the actual Docker file I used to create the image. You can customize it if you want to. And the cache folder will be used by Yocto or by Bitbake to maintain caching artifacts between Docker instances, so you speed up the process. We will also be talking about this in detail further on. Okay, let's go ahead and clone the repository and then download Yocto. So we enter the repository directory where it was cloned, and we run the start script. Okay, we're in the Docker environment. So the first thing to do is actually download Yocto. Now you could download Pokey directly, but I have a script that helps us do that, which is clone Yocto, and what it does is just creates a directory and downloads Pokey along with the meta-raspberrypi and the meta-open embedded layers. So let's use that. And let's give it a directory name, like workspace. I'll be back once this is done. Great, we've downloaded what we need to start building our first image. So let's go inside the workspace directory, and we're going to source the Pokey open embedded init script. Okay. Now there are two things here worth noticing. The first one is that you always have to enter the Docker environment. Just as an example, I'm going to exit the Docker environment. Okay, so I'm outside Docker. If I want to go in again, I have to use the start script again. And then the other step that you always have to take before starting to issue Bitbake commands is to invoke the open embedded init script to source it. So I'm going to do that again. Okay, so these two steps we always have to do before issuing Bitbake commands. Now, what did this init script do? This init script creates and puts you in a new directory named build by default. You might specify a different name by specifying the directory name after the script name, such as, so if we ls the current directory, so it created the build directory, but as an example, let's give it another name. Let's give it the name my build or something like that. Okay, so as you see, it created that directory, so that's the usage of it. So let's just take a brief look at the content of the init script. So you have a comment here regarding the usage. As you can see, they source it, and then you have an additional build directory parameter. One thing I did forget to mention while we were installing Docker in Ubuntu is that you have to use bash. It's the most compatible shell. So normally Ubuntu has a default shell set to dash. You have to replace that with bash, the instructions of which you can find online. It's easy to find. I don't think it's worth going into super details, but it basically just sets some environment variables, such as the open embedded root if it doesn't exist already, and it ends up sourcing another script which we can take a look at. And this one also sets some variables, some of which we will discuss later. It sets the build directory, which is the directory it created that we specified, or the default value. bitbake environment extra white, what this does is basically a whitelist for which variables of the environment variables will be considered to take into effect if we define them, versus the built-in bitbake variables. Again, this is not important, it's just going through the script so you know a little bit more. So I'm going to delete the folder that we had created previously because I'm going to use the default name. Now, one thing that might confuse you is the context in which you are in the shell in the terminal. So in this case we are in the Yocto environment. Once again, if we exit it, this is no longer the Yocto environment, this is your host environment, and you shouldn't issue bitbake commands here because they will probably fail. So once again, just start script goes into the build environment, then we have to source. Actually, it's inside the workspace. Okay, we're in the Yocto environment. Now, these files are actually available in your host system. So, for instance, I just created a new tab for the terminal. Now, in my host system, which is outside of Docker, I can still access the files. And sometimes it's useful for just editing because you have more advanced tools, you have graphical editors, whatever. But whenever you issue bitbake commands, in that case, you have to do it inside the corresponding environment. So let's just look at the layout that the script created. Let's go into the build folder. It's very simple at the moment. We only have a conf directory, which is quite important. Inside that directory we have bblayers.conf. Now what this file does is specify the layers that will be included in our environment. Then you have the local.conf, where you can configure basically everything in terms of global variables, and the template.conf, which is not very important. So let's let's open the BB layers to take a look at what it's including at the moment. Okay, so as we can see, this is basically including whatever is inside Pokey, which is meta-Pokey, Yocto BSP, which includes support for some platforms such as the QEMU platforms, or the BeagleBone is also included support for the BeagleBone, and the Edge router. And this meta layer is actually the open embedded core layer. Likewise, you can also take a look at the contents of the local.conf file. So right off the bat, we have a very important variable here, which is machine. We'll talk about the syntax as we go, and later on in specific. What the machine does is it basically picks off the board that you want to build the image or whatever target for. In this case, the default is set to QEMU x86, and this notation means that if no value exists for this variable, it will be set to QEMU x86. DLDIR is also another important variable, and this points to the downloads cache, which we will customize to point to our directory, the cache directory. The same thing for sstate. We will also change this soon. What else do we have here? The distribution, which we will always be using Pokey. So unless you download another layer which contains other distributions, Pokey is the default. By default, the packages that we will build will be RPMs. SDK is only if you're actually building an SDK, which we will do later on, but not at the moment. Extra image features. So by default, we have the debug tweaks, which basically means that the image is ready for development. It doesn't have a root password, and there are additional applications installed. Now, whenever we want to know more information about something, I really recommend consulting the documentation. So let's take a look at it in this case. I already have it open in image features, and you have a lot of details here. You have some of the built-in or baked-in examples for image features and image features, extra image features. Both are quite similar. It's just that extra image features is normally included in the local.conf, and image features is included in a recipe. We won't go into details. I was just showing you what's the process of discovering something if we don't know, and we don't want to know more details about it, at least what I normally do. So let's build our first image. We have some build parameters, and also don't forget to switch into the Yocto shell. So this terminal is my host terminal, and I have another one which is in the Docker environment. Now if you're going to be multitasking, doing other things while Yocto is compiling, you might want to configure following variables just to limit the resources Yocto uses, since it's pretty heavy compiling everything. So the first one is bitbake number of threads, and what this sets is basically the maximum number of simultaneous packages bitbake will build. In our case, we can set it to 8, or which is the number of threads that we have, or 4. It depends on whatever you want. And the other one is parallel make, and what this is equivalent to is the -j passed to the GNU make command. In this case, I'll just leave it at 8 because I have 8 threads. Now if you don't care, Yocto just uses the maximum amount of resources it can, and that will just speed up the environment, the build time. So in this case, I'm just going to unset the variables and just let Yocto, or bitbake rather, just use the defaults. I think it's also wise at this time for us to configure the cache paths so that it will speed up consequent builds. Now the start script for Docker mounted the folder we were in /opt/yocto, and we actually have the cache directory present there. So we should just edit the conf local.conf caching paths. So the first one, download directory, just set it to the path that we're using. What was it? Yes, so it's Yocto cache downloads. And the other one is the state directory. Let me actually see what the actual path is. Okay. Another major variable is the machine variable, which is the target to build for. So that's configured in local.conf as we saw previously. Now the default here for Pokey is QEMU x86, which is fine since we will be running QEMU after we build the image. If you want to know what options do you have, first of all, as we saw in the comments here, you already have several hints to what you can build for at the moment without any additional layers. But if you want to actually see where those where does that originate from, we can look at the Pokey machine configurations. So we can go back and go to the Pokey layer, and it should be in meta Yocto BSP forward support package. Machine. Okay, so we see here the origin of those values. Just as an example, let's look at the BeagleBone one. It seems quite complicated in the beginning, but there are some things that we can probably identify. So this is saying that the image will have to depend on U-boot. It installs the kernel modules and device tree support. What was the first one? Yes, so which package provides support for xorg, and some other parameters such as the U-boot variables. Now these are not really standardized. It depends on how each layer is configured. For instance, in this case it's including this file here, so probably this file will interpret the variables. So some of them are pokey variables, but the others are BSP specific variables. I imagine that these are. So that file will then pick up on these variables and do something with them. Now the QEMU layers are actually in the open embedded core meta layer. Now those were the machine variable options. Now we have to decide which image we're going to build. So if you remember from the beginning, when you actually source the... Now you can source this multiple times, it won't make any difference. When you actually source the init file, it gives us a banner here, which includes some of the common targets, which are, in this case, 2 images. The minimal image, which is... it includes basically just the kernel and a bootload and a very minimal file system, and the SATO one, which I believe includes a graphical user environment. Now if you want to see the actual places where these images are defined, you can, similar as we did with the machines, list them, going into sources pokey, and then we have a wildcard command to help us. Images. So we already have a bunch of images predefined for us. Now it's pretty easy to find descriptions without going into each image themselves, because they're in the documentation. Just as an example, so what image was this? Core image Western, a very basic Wayland based image, and it has some features here. SSH, hardware codecs, and so on. So it specifies Wayland. Now what I normally do is just Google for, in this case, imagine that we want to know what this image is about, or see some documentation regarding it. I really just go to the browser, type it in, and basically find the details online. So this was already in the... This basically just gets the description field from the actual recipe itself. If we go and vim it, so small image capable of booting devices, small image capable. It's basically just a more graphical way of figuring it out, figuring out what the image includes. So finally, as an example, let's just bake the minimal image. So bitbake, finally get to use bitbake. Let's just see. It has a lot of configuration parameters, but let's cut to the chase and just build an image. So it's bitbake core image minimal, I believe. Minimal. Now say you get something wrong, you know, a typo. You can still issue it, and bitbake will actually help you, as you'll see. So first it's parsing all of the recipes, indexing this. This happens if some recipes change, it has to redo this, but normally it's faster than this. Okay, so we issued a command with a typo, and bitbake actually instructs us that there are several targets. So there's no match for our target, but there are several close matching targets. So let's actually issue the command and clean the terminal. So this will take a while. I'll be back when this is done. So the image has finished building. I actually already had the cache with all of the elements, so bitbake didn't rerun all of the steps. So now we can, I believe that if you build it for the first time from scratch, you'll receive a message saying that you can actually run it using QEMU. If not, you can just follow along. So there's the run QEMU command, and we want to run the QEMU x86 image, core image minimal. Okay, so the first issue we encounter is the tunnel device. Now, if you don't want to run it with what this device does is basically just provide a virtual network device. So let's see what other options QEMU has for us. So we have this option slurp, which is basically provides networking at the user layer instead of using a TUN, which is a kernel level device. Okay, so another issue that we're encountering is x86 not available. So I actually, in the start.sh script, I have a resolution for this issue. But in order to use it, we'll have to exit the environment, the Docker environment, sorry. So this start script, it has the -x parameter, which enables x11 forwarding. Now, for X forwarding to be able to work, you'll have to have the xhost tool installed. In Ubuntu, I think it's called x11-server-utils, the package. And basically this controls servers. It controls permissions to the X11 protocol. In Arch, I believe it's at xorg-tools. We can actually take a look. So in Arch, it's package name is xorg-xhost. So yeah, let's start the script with the -x command, and why not use the -n also. So we enter the Docker environment, go to the workspace directory, source the open embedded init script. Okay, and run QEMU with the same command, and it should work this time. Okay, so we're booting our image basically. Let's just log into it. There's not much to do. In order to exit this, we can just close the window. If you don't get X working, there's no problem. I mean, we won't be using QEMU that much, although DevShell does need X, but we'll take a look at that in the future. QEMU does have an option to run without the graphical environment. This is no graphic. In this case, it's not an issue because our image doesn't have an X environment. Oh, wait, what happened here? Actually see. So no graphic here. What's the issue? And in this case, to exit the machine, you have to use a key combination, which is Control A and then X. It's similar to Picocom, if you're familiar with it. So Control A and X. Okay, there we go. We have built our first image, and next we will build a Raspberry Pi image. See you soon. So let's get started building our Raspberry Pi image. I'm in my host environment. Going to start the Docker environment again. The workspace. And I could build the image inside the existing build folder, but I'm going to create a new one. And we'll then copy the cache settings to our new environment so they get reused. They have the cache in common. Okay, so this is pokey OE, and then I specify another build directory, a new build directory. Now the first step we have to do here is add the Raspberry Pi layers to our BB layers file. So if we take a look at it at the moment, it only contains the pokey stuff. So let's go and add the Raspberry Pi layer. So if you remember, the clone Yocto script that we used in the beginning did clone it. Let's go to the layers directory, So we do have the meta-raspberrypi layer here. Let's just copy this and insert this in our bitbake layers file. Okay, there we go. So now bitbake will look and include the Raspberry Pi layer. Let's go back to our build folder. Okay. Okay, so since we have a new build directory, we have to repeat the customization, the build customization in local.conf. I'm actually not going to do that inside the Docker container because I don't have vimdiff installed there. Oh yes, and by the way, if this terminal is, if you're not familiar with this terminal, this is Yocto-Docker. It's just my terminal that I'm using at the moment. Just so you know, because I do switch tabs, and that might be confusing if you're not familiar with it. Okay, so let's just copy the caching configurations, for instance, between both. I'm going to use vimdiff. So you can use a meld or something like that if you want. Conf, and then this one, and then the Raspberry Pi. Okay. So I'm gonna use this basically to just copy over these settings and the S state. Here we go. Okay. Now I'm going to go back to the Docker environment, and we basically need to customize the machine, right? Because we're building for the Raspberry Pi. So what options do we have? Well, we can just inspect the conf / machine folder inside the meta-raspberrypi layer. You'll soon get familiar with the layout. So meta-raspberrypi conf machine. Let's just ls it. So these are the machines that we have available. In my case, I have the Raspberry Pi 3, so I'll be using that. So okay, so this is the name of the machine definition. You can actually go and edit it, see the contents. Okay, there's not much being customized here. That's fine for now. Let's just build the image. Oh yes, and okay, so let's just actually copy the. It's actually the Raspberry Pi. Sorry. So the machine name is actually the name of the file, excluding the extension. So conf local. You can specify the machine variable directly like this, or even not export it, just define it and then run the bitbake command. But I do prefer to include it, hard-code it in the local.conf, because we won't accidentally run bitbake under the default value that's set in local.conf. So let's set this to Raspberry Pi 3. Don't need this. Now let's talk about the images that are available. As like other cases, we can inspect which images are available to us by exploring the layer. That's Raspberry Pi. And then what we have here, recipes. Sometimes they're in recipes dash images or recipes dash core. We can always grep for it, obviously. Now, what do we have here? Raspberry Pi basic image. That sounds good. Paste this image on core minimal. Okay, so this is including this. It's basically just customizing the core image minimal, which was the machine that we built for QEMU, if you remember. And on top of that, it adds the SSH server, also a splash screen, installs the kernel modules in the rootfs, and then this is so one of the bitbake steps is do image, and what this is doing is prepending this code to that step code. So, and it actually, we can see right now that it will basically tell us that this image is deprecated, and we can just use core image base instead. Just for example's sake, let's run this image. Let's build this image. So I think we've already changed the machine variable. Yes, so it should be fine. So we can just fire off a bitbake and build that image. Now that message should come up, unless we did something wrong. In that case, an error message should come up. So the process completed, and as we suspected, we got the deprecation warning message, and we can also see that it had a total of 2,562 tasks, and 1,802 didn't need to be ran because we had already created those when we built the QEMU image. So let's just go ahead and build this core image as it suggests, and it will probably be quite fast because most of the components are already built. Okay, so the process is actually taking longer than I expected, probably because some base configurations on some base packages changed, so a lot of them had to be recompiled. And we have many other components, probably to support Bluetooth and such. What I wanted to focus on now is just the build configuration metadata that we hadn't discussed before. So you can see the bitbake version, the build system that you're building on, and obviously the machine, the target, and the pokey distribution. Okay, so we're at the end stages of the build process here. You see that the do-refs task is currently being run. And then after this, you have tasks such as do image. Okay, so the build process is complete, and now we can flash our image. The image is located in tmp deploy images. Then we have the machine name. So inside of this directory, cd into it. So this builds several rootfs. We can then narrow down what the target rootfs types that we want to build, but for now it's building an X3 Raspberry Pi SD image, which is basically an image that's ready to DD into a SD card, a tile of the rootfs, and other components such as the DTBs for the various variants of the Raspberry Pi, and also the Z image and bare boot, I think. So there's the boot files. So what we can do now is just DD this file into a SD card, insert it into the Raspberry Pi, and boot. I'm going to insert now as a USB drive. Now the USB drive doesn't appear in the in the Docker instance, so we will have to do this process in the host environment. So I just open another terminal. I'm at my home directory. Don't be alarmed because I just have one folder in the home directory. It's just that I created this user and I am using it, so I don't have anything else, any applications or anything in my home directory. Okay, so we can enter the directory where the image was built, which is in our build. No, it's actually in the RPI build. So tmp deploy images and machine name, which is Raspberry Pi 3. Now we can search for the Raspberry Pi image format. So previously we first built the RPI basic image recipe, and then we built the core image base. So I'm just going to choose the latter, and in this case I do have access to the USB drive. Just be careful using DD. It's not uncommon for people, including myself, to accidentally delete a system hard drive or something like that. So it was core image. What was it? Input file is this. Output is the USB drive. Let's give it a byte sector size of 10 megabyte. Status. Okay, that should be. Oops, it's actually the other way around. Okay, once this is complete, we can then take the SD card, insert it into the Raspberry Pi, and it should boot. Welcome back. I hope the Raspberry Pi image booted fine. So next we're going to look at Toaster, which is a web UI to customize and build images. So let's get to it. So we're already in our Docker environment. Let's go back to our build folder. Now, in order to use Toaster, you have to set up a Python environment and install Toaster's requirements. I don't know how familiar you are with Python, but so the first step is to create a virtual environment with Python. We could install the requirements system-wide, but remember that once you exit the container, since that system volume isn't mounted with persistence in Docker, you'll just lose it and you'll have to do it again all the time. So we're just going to create a virtual environment in our current directory. Actually, I'm going to use the tool because I thought the module was available, but it's not. Okay, so this is creating the virtual environment. If you're not familiar with it, you should just Google venv Python, and it's really simple. Okay, we activate the environment, and then we install the requirements. So this should be in the Pokey folder. Okay, so the requirements are installed, and now we can just run Toaster. So what this is doing is starting Toaster, and it's giving this host address, which means provide access even externally, so it's on all interfaces. Otherwise it would only be in the local host interface, but in this case we want access through the host system, so we have to specify that. And then comes the HTTP port that we want to use. Okay, so it should be starting. Okay, so finally the Toaster bootstrap process has completed, and we should have access to it. So in order to access to it, we have to actually see the IP address of the Docker instance. In this case, it's this address over here. I'm just going to go to the browser. So it's on that IP address, and the port that we chose was 8000. So there we go. The main landing page for Toaster is as we see now on the screen, so it shows stats on previously built images. In this case, I had an image that I cancelled. This was an image that I basically terminated, so there's no status on that one. This was actually an image that a recipe that I set to build, and we actually just finished now and got an error. You can actually see what it is. Okay, so Toaster in this case has an issue because it's trying to use Python. It's using Python 3, but it's compatible with Python 2. So we can probably fix that at a system level in our container. Okay, so in terms of what Toaster provides is really a complete set of a complete interface to create new images, customize existing images, and so let's create a new project just so we can see. Hub Shuffle project. Okay. Let's use master, why not? Okay, so we can just choose the image, the machine, I mean, sorry. So let's just go for an exotic one. I don't know. Yeah, let's go for the Arduino. Okay, so we set the Arduino. Let's choose a different distribution. Guacamayo, I don't even know what that is, but let's choose that. This is just an example. Okay, so these are the layers that that our image contains. Let's choose a distribution. Oh, so we've got to choose the Guacamayo one. We can add more layers if we want. We can also add a custom image, which we'll see in a moment. So okay, I'm kind of going crazy here because a lot of these things probably don't work well together. So image. Let's say we want to build the old winner image, which we included. Where is it? Here it is. For this configuration. So yeah, you can basically do everything through this interface, but on this course we will focus on the command line usage, just because you get to know the image much better. So you could set up the cache, which we didn't, but we should have, because otherwise it's just going to take longer. Image FS types. Actually have checkboxes so you can select which ones you want. Distribution, add your own variables, and so on. Documentation. Yeah, so it's pretty good. I mean, if you already have a set of metadata that you created and you just want to build new stuff, or want someone else, you have a build machine and someone else can just use the web UI to build images, it's quite useful. One cool thing Toaster has, and I don't think that through the command line you can get the information, it estimates the image size, and yeah, you can basically just edit the recipes in order to tweak your image. And you can actually also run the image from Toaster. So as the final section for this chapter, let's do some basic customizations on the Raspberry Pi image. The documentation has some steps, some customizations that we can do. We can just, I'm in the meta-raspberrypi layer directory. So they have this documentation, which I'm just going to open in the browser. So there are quite a bit of customizations we can do. From boot delay, enable, disable splash screen, the amount of memory reserved for the GPU and such. I think we can even set some overclock settings. For this case, we're just going to enable the UART. It's quick and simple change. So for the Raspberry Pi 0, 1, and 2, the UART is enabled by default, but not for the 3, which is the version that I'm using. And as they say here, you basically just have to set the following variable in local.conf, and which we will do. So I'm just going to copy paste this, enable UART line, and basically just add it at the beginning, can be anywhere. and I'm going to rebuild the image, and then we'll boot the Raspberry Pi and hopefully see if the serial port is working. See you in a bit. Now that the image with the UART changes has finished building, we can reflash the SD card. So I've inserted the SD card on the Raspberry Pi and I'm going to boot it. First I'm going to open the terminal. By the way, if you need help regarding that, you just need a serial to USB converter and hook it up to the right pins. And you can find the pinout diagram quite easily in Google. So here, the UART pins are 8 and 10, and then you have to connect probably ground also. Probably no, certainly. Right, so I've already done that. I'm going to power on the Raspberry Pi, and you should see the kernel messages and the command line after the kernel is done booting. Okay. Right, root, no password, and yeah. So you can go through the other customizations, just try around and build your own images if you want. Let's go through a couple more customizations. One of them is, for instance, enabling the I2C. So if you go to the documentation, you have to set the enable I2C variable, and this variable then gets passed by the code that's in the machine code for the Raspberry Pi, which ultimately ends up passing a parameter to the DTB file. So we enable I2C, and then there's another variable which we can define here, which is image install, and we can add to this variable and say we want to install I2C tools and then Vim, since we only have VI installed. So after setting these, we just need to write the file and regenerate the image. Okay, I'll be back when this is done. So I actually got an error while building the image. We can see that BitBake says that nothing provides I2C tool. It's actually a typo, it should be I2C tools. Let's see what BitBake says if I specifically try and build I2C tool. So it does help us in the sense that it shows us the close matches that we have, which is helpful if you don't want to go and grep for the recipe or something like that. So we just need to go back, edit the file again, fix that, and rebuild. So I actually got another message, which is the same as the I2C tool one, but in this case I did try BitBake Vim, and it seems that we don't have a recipe that provides Vim. But actually, when we ran the clone Yocto script, we added an additional layer, which is the open embedded layer. So we can add this layer, and this layer actually includes a recipe for Vim. So let's try that out. So if you remember, we have to edit our BB layers file. Oops. And I'm going to add the meta open embedded layer. So I'm going to try to build it again. This time I'm actually going to use an option in BitBake, which is a dry run, which doesn't actually execute the tasks. I don't remember which parameter it was. I think it's -n. So this just goes through the parsing of the metadata. So let's try that. So BitBake Vim -n. Okay, so it seems I'm wrong again. Bitbake is complaining that it can't find the conf /layer.conf, which basically tells Bitbake that that directory contains a layer. So let's actually go into that layer, into that folder, sorry. Yeah, we don't have a conf file. Let's take a look at the README. Okay, so this is actually a collection of layers. We can search for the Vim recipe, which I know exists here. Okay, so we don't want XFCE, which is a graphic user interface, a window manager. So we just want to include this open embedded core layer. So let's go back to our folder, to our build folder, and let's edit the BB layers file again, but in this case just adding meta-OE. So let's go through the dry run again. Okay, it seems we got it right, so let's run it for real. So it installs it in and makes a new image. So core image base. And I'll be back once this is done. The build was successful, so I'm going to just write the image to the SD card and put it on the Raspberry Pi. Okay, so the Raspberry Pi has just booted, and sure enough we have Vim available. In terms of I2C, we can try and detect a bus. So we actually have to mod probe the I2C dev kernel module. And a controller is actually detected. No devices are detected though. So yeah, that's it for the Raspberry Pi image customization for now. In the next chapter we're going to look into Yocto and Bitbake in more detail. See you then.